Welcome to Renaissance Charge Videos. I'm Rick Friedrich, and today we're going to look at the 4-pole Mini as it is presently right now. There's a number of you that need to assemble these, so I'm going to go through some of the basics here of that beyond the instructions that you get by email. Anyway, what we're going to do is glue in these magnets here. There's no other way for me to do these magnets, these rotors, other than to glue them in. So what we do first is distinguish between the North Pole magnets, the North Pole of the magnets, and the South Pole. So you'll see usually these lines here that indicate the North Pole, or the other way you can do it is that if you have a compass, the North Pole of the compass, or the north facing pole indicator, is actually a North Pole pointed to south, a south magnetic pole, so therefore it reflects away, or attracts to a south pole, magnetic pole, which is the North Pole actually, or on a magnet, the south magnetic pole of the magnet, or repels away from a North Pole. So that's how you're going to determine which way of the magnet. But a lot of these now have stripes on them to indicate which one is the North Pole. So now what we want to do is put a very little dab of epoxy. So you don't need very much at all, very tiny little bit of epoxy, and you just mix it together, and I would just do enough for one rotor at a time, and then you can have, so what you want to do is get some clamps to hold these magnets in. What I do usually, these ones are already glued in, so I'm not going to show that, but I usually take, what we'll do in a minute, I guess I'll show this. I'll stop the camera here in a minute, but we should have some clamps, wooden clamps for wood or whatever, or you could just use some vice grips if you had to, and then just use some wax paper while you're doing this, and then put your glue in as I'm going to show here, and then you can just use the flat side of the other one. In this case, the magnet's already in there, so and then you could actually press it down, or get a nice piece of wood that's flat, and then just hold it there for a couple hours in a warmer room, and then do the same thing for the other side. So you want to have one side on a single stacked motor here, where the magnets are facing out one direction, and then the other one the opposite. So one will be a North Pole facing out, and that will be the top of the top rotor. So the North Poles are facing downward in this case, and then that means the flat part of this has a South Pole facing up, and that will be for the Hall switch here. So then the other one, of course, it will be facing the opposite direction, and the magnets, the South Pole, will be facing up. So then the bottom will be facing North Pole. And that's just simply because this Hall switch has the face of it facing downward on top of the rotor. That could be positioned differently. So it's up to you the way you want to do this, and I'll explain the coil orientation as well. So it's not a big problem. If you make a mistake, you can move it around and change it around. But I'm going to go over the various steps. So that's kind of the first stage. What we want to do is put a little dab of, don't use crazy glue. It's easier to work with crazy glue, but you have to do it really quickly. And then if you do use crazy glue, you can always get the magnets out by refrigeration, by putting the rotor in the refrigerator overnight. But we want to do it properly with epoxy. So you put a little dab of epoxy inside the hole of the rotor, and then you'll put each magnet in one at a time. So you do a little dab. If you're really good at it and you've got a nice press where you can press these, most of those magnets fit in loosely, and that's why we have to glue them. Some of them need to be pressed. So just a little tiny press that we usually do them. Now most of the time we've done this for everybody, but for the unassembled ones we haven't. On the assembled ones, of course, we do this for you. So what you'll need to do is press them down so they're flush. So you don't want to put too much glue in there, and so they stick out. If they stick out a little bit, it's not a big deal, but just make sure you hold them down until they fully dry. Otherwise they'll pop out later on, and once they're frozen in there, then you would have to actually destroy the magnet with a sharp piece or whatever to get that magnet out and start over again with another magnet, which I don't provide any extra for in the kits. So anyway, we want to do that, and then what we want to do is, I'm going to show this in a minute, we want to put more over the top just so that they don't come out, and just a little even layer over the top. So I'll get some gloves on now and I'll show you what I'm talking about. So now we've got the wax paper, we've got the gloves on, we've got the pen that's got Richard, of course, as my little stirring stick, and I just put some of this on a piece of cardboard, and what we're going to do is stir it all up in a well ventilated room, and stir it all nice and good so that you've got both items mixed thoroughly. And then we're going to apply this a little bit at a time. Just so that it goes over each magnet, and it will kind of, if you apply it into a little circle here, it will smooth out over time. Just make sure it covers all the edges. Not too much, otherwise it will rub up against the coils. So there's no point in showing all of these. We'll move on to the next step. So the reason why we started off with the rotors first was because we wanted to let them dry and we could do other things while we're waiting. So what we're going to do is get the 4 feet. So this is actually a longer rod than what's provided. So let me take these. So you'll have quite a few nuts and washers here to deal with. Anyway, they're not going to be on there, but I wanted to show all the different parts here. So the first thing you'll want to do is put one nut on, and actually we'll get rid of this one altogether. All these, let's just start off. Of course the one that I have, you'll see, is already assembled. But what I want to do first is we want to put this nut on, and then we'll have, and that's going to be for the bottom of the bottom end plate as a support. And then we'll throw another one on here, and then I'll get the lock washer and then the flat washer. And then we'll put the foot, one of the feet on, and then you'll notice there's a cavity there, and we'll put this one right on the end flat. Now these rods are all not exactly the same, but they're pretty close, so there is a little bit. So what I'm doing is pulling that so we've got the nut inside. right? And we don't want to turn this nut by turning the foot anymore. So what we're going to do is go down, and then I'll take a 9mm and I'll just turn that, which I didn't have right with me right now, but we turn that tight so it compresses it. So what we have here is 9mm, and you could really use 2, but you don't have to have 2. It's kind of a little bit tricky to do the first one, but you can tighten this later on once you have the other nuts in place. So you just want to tighten it so that it compresses that and it kind of bulges a little bit. So you're going to have that one kind of compressed in there, that washer a little bit, because if you have any vibration, eventually this could come loose. So then on the top, what we do, so this is obviously facing upwards. So what I do is I have the flat the flat washer, and then the base plate, and then I put on the top of the plate, I put a lock washer down, and then a nut, and then another nut for the top plate, and I use the another one of these lock washers on the bottom of the top plate. So you got another nut, lock washer, plate, and so the top of the plate I add a flat washer, and the reason for that is because one of the parts here is going to be for the loom, where the Hall switch is going to be mounted. And so depending on how tall you make these stand above the plate, you can maybe still put the flat washer on top of the loom. You don't really need to do that. Like in this case I didn't do it because I made it really no more room to put the nut on there with the loom. And the reason why I don't really want too much of a bolt sticking up, because if I'm turning this, I could catch my hand on that. It's kind of sharp. So right now we don't have any kind of caps that go over top of that, but you can always file them down a little bit. Anyway, it is a kit, so that means you can do what you want to do with it. So again, we'll go through this. You can see the same thing that I just showed. So you've got 1, 2, 3, 4, 5, 6 nuts per bolt. So we've got 24 nuts and 4 bolts, and we've got lock washer, flat washer, no washer down there because you don't need one. But anyway, then we have nut, flat washer, lock washer, nut, nut, lock washer, flat washer, nut. And of course here, same like I told you. So what we want to do, this is already going to come like this. All you have to do is add these 2 wires here from the coil. And I usually like to have them connected right close, but I think we're providing that now with some extra 2 wires from the coil, so you can have the circuit board more removed from the motor. I mean, it's nice to have it mounted to the motor, but you never really know what the EMPs from the coils are going to do to that Arduino. I think it's pretty rugged, but over time you never know. So having a little bit more of the distance might help that. But you can see the Hall will already be provided with the wire. So this is like a 12 gauge wire here that we use to wrap around the so it's providing support for the Hall so it doesn't wobble around and move on the heat shrink side, but then it comes out the back here and you just wrap it around so that you can wrap it back up and give it even more support here. So it's up to you how you wrap that. I didn't do a very good job here, but of course this one I had to take the rotors out. So what we're going to do is find my parts, which I apparently don't have here, and explain the rest of this bit by bit. But I guess before we get to that point, we really need to talk about the coils. Now this was the first prototype coils for the new coils that we have, so it's got a lot of glue on it. It's messier than it will normally look. But what you want to do is determine the inner from the outer wire and determine the polarity of the coils. But as long as you do all the coils in the same direction, you're good, because you can always flip the rotors on either side. And before we even deal with the shaft, we don't need to deal with the shaft and the rotors until the very end. But we want to put, with a file, we want to file down two flats on either side, completely 180 degrees apart. We'll do the bottom one first, and then we'll do the other one up top. And of course you could move that around. Like if you want this to be further up, you can make it really short here, or you can make this rotor, stick down. If you don't want this as tall, you can have that going close to the shaft sticking out, and maybe you want another pulley down here instead of up there, so whatever. You could do a longer flat on all these. And then once you do the bottom one, you definitely want to do enough flat so that the set screws, when they score into the shaft, you're able to, when you loosen them, able to still pull the shaft off. But if you don't flatten it at all, then the problem is trying to pull that off. It's very tight fit, very, very small clearances, and so it is very difficult to get off. So take the time to do the flats on there. But before we get to that, what we essentially have is 4 motor coils and 4 generator coils. And at this point what we're doing is we're making the motor coils the corner coils. So we've determined that in this case the top wire, which is the outermost wire, is the red wires for all the 4 corners. And so this will be the top one, and the bottom one is the black wire, and that's the innermost wire. That means that's the wire that starts with and turns around. Now in some cases you can have a polarity difference depending on when you're watching this video. If you have maybe an older coil that maybe it was reversed around, where the black wire was on the top, the top wire was on the bottom, so, or the black wire, the red wire on the top or the bottom. But essentially what you're doing is you're taking all 4 wires, and you can just do this for yourself. So you have, say you have one coil here, and you before you mount it, you determine which side, you determine the polarity of it. So what happens is you're taking, a more dead battery, 12-volt battery. You don't really want a big battery or a really charged battery, but essentially a small battery can do this, where you connect up one end. So if this, you determine that this is beforehand, the outermost wire is the red wire. So let's hook that up to the positive pole of a battery, and then just tap this end, the other end, maybe with a wire clip, extension clip. Then you can tap that onto the negative with a magnet being held. So one hand hold the magnet, one hand hold the terminal, and tap it. And it should repulse a north pole away. Let's see here. Yeah, because the rotor is facing downward, with the north poles facing down here. And it should repulse it away, because this becomes a north pole when you make polarity connection with battery. So if you got it backwards and you want to run it the whole way other around, then that's fine. It doesn't really matter as long as you understand that this is a repulsion motor. It's not a traction motor. And so that's that. It should be straightforward from my comments. And what you want to do is start with the bottom plate. Put all of the rods with the feet like I had just described with this one. So get them up to this point. Well, I've got a little bit extra on there right now. So just get them up to this point, and then put them all on the plate here. So now obviously this one is longer. This was not for this particular motor, this rod, but you want to kind of measure this distance here, and you can tell by the height of the coil minus the core. And so now you're going to determine, well, I need a little bit of space up here, and that's where you're going to adjust this nut to. And then just make them all the same, and then you'll see a couple of them maybe be slightly longer than the other ones, so then you'll just compensate and have one stick out a little bit further than the other one, or whatever. Or you could make the one extend a little bit further out here if it's longer. So you'll tighten these all down, put the lock washer on the top of this plate, and then bolt down, screw down a nut on top of that and make them all really tight. And then what you want to do, so you'll put them on a flat surface and feel that they're not wobbling. If they are, then you'll just have to adjust them around until they're all equal. And then what you want to do is start putting your just the 4 generator coils in first, especially with the bigger coils that we have. So sometimes we do the bigger coils, sometimes we do the smaller coils at this point, just based upon availability of what we can get. So again, what we're doing is the generator coils are on the center of each plate, so 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock. And so what we want to do in that case is, again, put them all in the same direction. And like in this case, you can see the stripe, they're all on the top side. And so now we're going to make a series connection between them. And you don't have to. You could have each coil doing something else on its own, but I usually make these in series. So you can see the series connection comes out here. And what we have here is the bottom of this coil. Oops. So this front coil, the bottom of it is, in this case, the black wire. And again, this is not, these are AC outputs, they're not DC. So you could use, I provide the wire, this wire for you to use. And then the other wire is coming from this coil over here, the top side. So then this bottom of this wire connects up to this top one. This bottom one connects to this top one, this bottom one connects to this top one, and then you have a series output. So then once that, you solder those in before you're going to put this base plate on. And then you can do this afterwards if you can still reach it, depending on how much wire length you have here to work with. So then what you're going to do is put your motor coils in, and then you stick all the motor coil windings outward. So you can see these ones right here are facing outward instead of inward like the generator coils. And then we can have these extra wires come all to a common connection here and here. So the red and black wires come out here and here. So you do that all the way around, and then you can put the make sure you put the next nut down, followed by the lock washer. Put it further enough down, and then you put the plate over. And of course, I forgot to mention the plates. You have to also glue a little dab of glue on the inside of the bearing, which this has already been done, so I can't show you that. But you don't want it oozing out. So these base plates should be done at the same time with the bearings. But notice that the bearing flange is out on the outside of both of them. So make sure you don't mix that up, because the rotor through the spacer is going to be compressed. The bearing is going to be held against the base plate with the flange through the rotor. It's locked in there. But if you have it reversed, you can't do that, and then it could eventually push the bearing out the other side, you know, if the flange is on the inside. So make sure you do that. I've done it enough times to wondering where's my brain. So it can happen, and then you'd have to kind of take it all apart and that's a nuisance, and some of you will do that, I'm sure. I'll hear about it. Anyway, what I do is I use some hot melt glue just in and around the coil, the laminations, so that none of these laminations ever come loose. And I do that a little bit on the top, but you don't want to put too much on the top, because there's only so much clearance if you're only using one spacer. And what I'm doing now is more recommending, I mean, it depends on what you want to do with this motor. If you want to make it a torquier motor, you have only a single space. But when you're dealing with a double stack, we're just going to assemble them from now on as a double spacer in here. So in other words, the magnets in the rotor are further away from each other, and so there's less of a magnetic lock and drag. So it's less torque, but it will spin a lot faster. So for the single stack, I'll probably just end up leaving it with a single spacer in there. Now the spacer goes in a certain way, in which the flange is on the outside in these directions. If you can see my thumbs. And that way, if you have the flange side of the spacer, it would ride against the non-moving part of the bearing. So you want the smaller end of the spacer to fit on the shaft, touching the bearing, and then the flange side will fit on the rotor, and I'll show that when I assemble the rotor here. So then you've already got the circuit board assembled for you, and there's two more things to do, or a couple more things. Putting the clips on all the cables, but you want to do that first before you attach the circuit board and these wires right here coming from the motor coils to the board. So first, deal with all the miscellaneous. So what we have is 3 sets of wires here. So the smallest ones are the 12 volt. They have to be 12 volts, and you need to keep a charged battery, just a small battery. And this will power the Arduino, the gate driver, and the gate of the FET, which don't want to spike on them. So that's why we do this separately. Now we could do a voltage isolated deal off of a DC converter. I'll probably end up doing that. That just is kind of like 100 milliamps is really all we need, I think. We're not even running that very much, especially once I upgrade this to show the PNP basically reverse protection part. Instead of what we're using is just a straight diode here, which does draw power or it reduces the efficiency, and it also is dropping the voltage, of course. So the smaller cable gets these smallest clips. The input wires get the medium-sized clips. They're not as important as these 50 amp cables going to the charging battery. So how do we determine that? On the single stack, we have 3 different sets of wires, and they accordingly correspond to the smaller and bigger clips. And you can see the input positive terminal, to back up here a little bit, the input wire terminal is connected with the charging negative terminal. The charging battery negative terminal and the input positive terminal are connected right here, going to the red wire from the top wire of the motor coil. So these will need to be connected, and I usually provide a heat shrink tube to cover that up, or you can use tape, and the same with here. And then what I've done here is provided a little capacitor. So this is kind of like a filter of sorts, and it's on the input. So basically I'm going to be running this with basically on the other side of the input battery. This cap is across, so it's as close as I can get to the coils and the circuit. So I have a red wire also connected into this connection here, and the black one is going to be the same connection here as this common bus bar at the back here. You'll see the Arduino input black wire is there, and then this is across the MOSFET, right? The source of the MOSFET, the S terminal. And then so I've got the capacitor also across there. So this wire will these two will already be soldered there, and then you just have to add this if you want to. So you've got the cap really across the input. So basically the other end of the wires on the input battery. So that's why we have this inductance coming from the battery through the wires, these wires right here, and I'm trying to eliminate as much of the inductance with the capacitance here. And so that is providing somewhat of a filter for a negatively charged battery. And that's another whole subject matter. You can watch my other videos on that subject. So really, you can put this Arduino back carefully, this on the board. So you just want to make sure you don't bend any of the little pointies here. And then you also have to have the space for this wire right here. And then what you can do is use some wire ties and hold these in. So again, you want to connect. Now the only things that you need to connect yourself on the board, besides that one terminal if you're going to do that, is this wire right here, this black wire now. So this black wire coming from the motor, the bottom wires, is going to go right into, oops, you can see, so these 2 feet, the 2 outer terminals of this diode here. This looks like transistors, but it's actually a diode. It's just got 2 legs to it, and they're going to come together. Well, they're already come together and put for you on the board. So what you want to do is place the black wire on that, and that's also connected to the center terminal of the MOSFET. You can see there. So be careful, in doing that, you don't make a big solder clump or a cold solder joint, which I've seen people do. And then I've just got a heat sink on this one, so we'll have different heat sinks over the years, whatever is available. And you probably, if you really want to get pushing this hard, you want to have a bigger heat sink than that. The hotter the MOSFET gets, the less efficient it will run. So that's pretty much it for the assembly. I'll show the rotor after it dries. I'm still waiting for it to dry. And we'll start running this and talking about more things, such as what we want to do with this. All right, it's been several hours, and what I have is the rotor looking like this. You can see there's a little bit of kind of like a bubble on this. So that will hold it. It's not coming loose between the glue underneath it and over it. This is pretty strong epoxy. You should probably wait 24 hours for maximum hardening, but they're pretty solid now. So I've got both of them done. I've got this Allen key that comes with it, and what we'll need actually is the wrench in addition to this Allen key, because you can't really do it with your fingers very tight. So what I talked about already was a couple things here. So what we'll do, so what we have here is, what I did is I drew a line, and then I went down and drew the line on the opposite side, and then I'd put flats on. Once I put this side on and this rotor on, then I can hold the rotor in position, and I'll show you that in a minute. So now we got to look for the right rotor, one without the stripes, so that the south pole is facing upwards. And of course, I wasn't doing it right already by failing to add spacer. Don't do that, because it will be kind of hard to put the spacer on. Notice the flange, like I said, is facing the rotor so that it's not rubbing against the bearing, only the part of the bearing that is so in this case, the only part that, anyway, whatever, you know what I'm saying. So what we're going to do is make sure this set screw is lined up. Well, there's two set screws that are lined up with the flats, and initially I will just hand tighten it, and then I'll tighten the rest of it. Because of the flats, even hand tightening it will be pretty strong, but you cannot rely on that as a permanent. You need to tighten it further. So I will do that. Let's see. Turn this off again. We'll need to do that again and again. So what we'll do then, so you'll notice that it wants to sit square. Oops. So that it's not completely straight up, the set screw. So I'm going to turn it slightly, and then I'll do the filing straight on so that they're lined up with each other, which is what I've already done, so don't need to do that any further. So again, you can see the stripes. They're going to go down, north pole facing down, south pole facing up, and you can see it's a pretty tight fit. And again, we'll tighten it. So what I did on this one, and you don't have to do on the bottom, but I've made the flats, this side, come out quite a bit further, so that if I wanted to put the 2 spacers on, which I will want to do with this one in further testing, then oops, so you can see it's pretty tight. So you gotta just make sure that none of your glue is touching either, well, you've got 2 sets of glue. You've got the epoxy and you've got the other. So actually I do have a problem here. One of these cores is a little bit too much, so I'm going to have to take that off and flatten it. You can see this core right in there. The top one is too close, so that's actually rubbing right now. Alright, I'm all set up, cleaned up the rotor, and positioned the hull actually before top dead center on this particular one with these coils. Usually it's after top dead center, so I have a different arrangement here than normal because I think the way the coils were wound. Anyway, this is my battery to run the gate driver. Again, we want this to be free of any kind of spike, which will never be completely, but it's good enough the way it is. Otherwise, we could run this off of the input battery through a filter, or what you'd want to do is have isolation DC converter, which you can get these little cheap ones, which eventually I'll probably provide for this kit. But anyway, so now we have the input battery, and that's sitting at 12.62, and then we have the charging battery, which is sitting at 12.53. And it's a good idea to get one of these little clamp meters. Make sure it's a DC, it has a flat line on it, and usually that will obviously have an AC option as well, so I have to select it. So I'm at the 20 amps and you have to kind of zero it out. So I'm going to look at the input amperage while I'm starting up here. So now all we have to do, this is how we'll turn it off on this battery right here. We don't want to turn it on while it's the rotator's running though. If we do disconnect it, don't disconnect it back on until it comes to a full stop. You could disconnect the input battery as well, but just do not disconnect the charging battery, because it will blow out the circuit. Because again, and I've covered this all in detail in my other videos earlier. This is more of an assembly video, but the whole idea of the charging battery is to replace the snubber system, the flyback diode, so forth, and use that wasted energy to charge a battery. So we're going to start this up, and you'll see, you know, there is, well, before we do that, we can see that there's quite a strong magnetic lock here, which probably should be a little bit bigger spacer there. That's why you know, I have the option of having 2 spacers in there, but we'll do this for now. Once it gets rotating, it loses that magnetic lock considerably. If we have the double spacer, it will lose it completely. So it'll be a no drag motor. Okay, so you hear a little click. It's a little thump, giving it a kind of a test pulse. That's what we do in the code. There's a number of things that we're doing with this code. that are kind of proprietary. One of them is the Liberty pulse. We change up the pulse every 1/10 of a second, and then we have some various protections. So if it gets down to too low of an RPM, it will shut off. It will stall out. That way, if for some reason it was binding and the motor was still trying to run, it would create a lot of heat and burn out the circuit. So we have a stall mechanism. So you have to have a minimum rotation speed, which is about 60 hertz or something like that. So again, now we're ready to go. You can see the lights are on. All I gotta do is give it a start. Well, let me turn it off first. Well, maybe. There we go. You can see the charging battery is charging, and we're at 3 amps. It's kind of backwards, but same thing on the 3 amps input. And now when we connect the generator coils, so there's AC on here. But watch what happens. It will speed up now. It will draw less amps and it will charge less. So this is quite interesting. But it will speed up when I've shorted the generator coils out, which is what we want to do more on the when we have the double spacers. So now I can reposition this Paul, and then I can turn up or down the throttle. And then what we do is, and I've already done this to these bearings, is lube them with the Bishop's oil whenever I assemble it. The unassembled ones, I don't do that with the bearings. So anyway, you can see it's still charging, 1281. Of course, the input battery is discharging. But now we can do something with this mechanical energy. And we can also load this down. So what we want to do, I'm going to turn this off so I can talk. So you can see now that it's not under load, you have the voltage drop like normal, but there has been some charging take place. And of course, we've got 0 amperage now. And so what we can do with this output here, so this output can be run through a variac, and I've shown this in previous videos, so I don't need to go over all that detail. The variac offers the ability to change the voltage output and to some extent the amperage. So ideally what we want to do with this winter, we get some more time, we're doing some other projects right now, but what we'll do is return to this, and we'll have the output of this, which is a higher frequency, of course, than your 60 hertz. So what I have is some variacs, an isolation variacs that will run at 400 hertz, they're rated for. And so that's where this motor is running at right now around. And especially when you load it down, it's going to drop in some speed. And then what we can do is run loads that are 400 hertz, which is like military and airport devices. So you could run, what you'd want to do is put a resonant load on this. So not talking about the Variac at this point. Now what we can do is run this frequency into an inductor and capacitor at the particular frequency, matching the frequency, and then drive a load off of that with an amplification factor because of the resonance. And that's really what we wanted to do with this generator coil output all along. And I've talked about that for many years now. So what we'll do, because I've been changing, some of the parameters of the motor, and so eventually we'll have the parts to do all that. But we've been focusing on two amplifications of the output. One going into this charging battery here, and that's what we call the third stage process. And what I've been sharing in my meetings is the true wireless figure 5 diagram, which is very small and people pass over it. True wireless 1919 from Nikola Tesla, to be specific. And if you apply that, and if you analyze that carefully in the context of the paper, and you go into in light of figure 10, which kind of is the fuller amplification of that circuit, which shows the secondary, is what I'm trying to say, then you will understand more of your options on the output of the motor output going into the charging battery. So for those of you who don't know what I'm talking about, if this is all new to you, we are charging another battery when normally that's considered impossible. We're not charging this battery from another motor, from another battery over there. These batteries are in series with each other. That other battery is just merely powering the motor, in which it's got a short circuit with itself and is self-discharging because of a closed loop. This battery, on the other hand, is being charged from the environment. You could call it the collapsing of the coil, but the energy is backwards, and it's also negative energy. Long story, you can watch my other videos if you want to find out the details. But what I'm getting at is the output to this battery, so there's an output diode, and after the diode, we're running that wire to this positive pole right here, this positive terminal. That is considered a one-wire circuit if we apply Tesla's information on that is process. So go to the True Wireless. It's talking about the one-wire circuit, no return wire, and there is 5 options. It shows 4 A, B, C, and D. Figure 5 A, B, C, and D, and really D is 2 options. So if you apply that along that wire, this is the secret, people. And I've shared this in my meetings, but since I'm not having any more meetings, I'm going to share these different things that I share at my meetings over time here as I have time. So a lot, like I've showed before, just running an inductor in series with that wire, and that's the basic level. But if you take it in the true sense, more ideal sense, you're going to do the Tesla circuit, where you have a parallel. Well, first of all, figure A has the diagram. So here's the wire going across, and you have a tank circuit which is a coil and a capacitor. So you have this perpendicular circuit. And this is what I've done a lot. I've never really shown that to anybody. But you run the circuit, and this is mostly for high frequency, but it can work in this case too. So you run the circuit where you run a coil perpendicular to the wire, and then you have a capacitance on the top. And what does that look like? It looks like a Tesla coil. The ones that you normally think of in a Tesla coil with the capacitance on the top, the dome, you think of. So anyway, that would be the primary, the coil, and then a secondary would be the output, right? So you can get into wireless if you're dealing with high frequency. In this case, we would be dealing with a parallel coil, and there's a whole bunch of arrangements that Tesla shows. Now, otherwise, you could have number B, you could have a parallel wire, parallel with this red wire here, and then a primary, going up to a primary, and then coming back down and paralleling the wire. So that is also B, 5B. And what I've done is I've drawn a diagram of this, which I guess I'll put in this video. And that diagram, I exploded it. I made it bigger so that you can really clearly see what he was drawing there and talking about. And then I coupled that with diagram 10, figure 10, which is showing you the 4 circuits in his tuned circuit system, which are all unsynchronized, but that's not what I'm talking about here. But anyway, you can see in that diagram the full circuit, which is showing the secondary off of the primary. Figure 5A, people didn't really understand it because they weren't thinking in terms of having a secondary off of the primary. And so when you go to figure 10, you can get that point, which we'll see in the diagram. So anyway, now you can run a secondary and power it. And that's why when you see in our black box, the video that I showed, the 2 videos that I showed a year and a half to, I guess 2 years ago now, or whenever it was, from the Chicago meeting from 5 years ago. So if you go back and watch that video, now you can get more of an idea of what's in the box, or your options there. So now you can see why there was no connection between the output, there was no electrical connection between the input wire, or wires, and the output. There's no solid connection. So it's, transformer based, but you have to consider what kind of transformer. So anyway, then there's another option of having the wires embedded. So you can look at C and D as options as well. So, but I think most people will be focusing on 5B in the True Wireless article from Tesla. So, what I was showing was also similar, where you run this wire into an inductor and then having a secondary or just a capacitance or just gating that out to a bridge or some kind of load like a battery. But the problem with that is that inductance in the line is a problem. It's too much energy and it's too unstable. That's kind of why I never showed it at first, because I knew people were going to be blowing up the parts. So without trying to get too much into the subject matter, I thought I'd just throw that in here to this video. It's not really part of the instruction video, but some of you will appreciate this information. It's extremely valuable. So anyway, when you have that inductor in line, which is you have to add that into your calculations and into all the different factors that it creates. So now that's really unstable. And you can see that wasn't done in the black box because of the nature of the output that was coming out in the tests that were shown to you. You can see the outputs were completely isolated. So they were independent, whether you were using them or not. They didn't affect the motor. Well, they didn't affect the motor that much. In other words, some of the energy was still flying back to the input, so the neon bulbs were coming on brighter. In this case, we don't have any neon bulbs because we're not using the transistor circuit with that neon bulb option on it. But anyway, when you have the parallel wiring, then you're picking up you're kind of more you're isolated completely. Not completely in the sense that it's not going to have an influence back into the motor side of the circuit, but it's less of an influence than an inductor would be. So anyway, you have several options there, and once you start playing around with that very carefully, I won't suggest using this as a test subject to get familiar with it. If you use some of the transistor setups, the cheap SSG circuit with a cheaper transistor, then you can play around and get used to that. That's how I learned and started with this. When you start using these more powerful motors, you can be blowing up parts a lot easier and be more frustrated. So anyway, but that's where we're going with all this, or we've gone to, I guess, a long time ago now. And once you get a feel for it, you can actually use this motor as a prime mover and then multiply the circuit out again and again and again, which is kind of what I was showing with the resonant coil kit. Now, this has to be in resonance now. This is a resonance process when we're doing that with Tesla's circuit, figure 5, A and B, C and D. In order to multiply it out again and again, you have to, have the right details. So you have to have a frequency matching an inductance and a capacitance. And so that's always necessary for resonance. And that's what you'd have to do for this. So those of us who know how to do this can multiply it out as many times the output. But you still have to factor in some phasing with the excess energy coming in, or have a sufficient load, to temper that. So there's a little bit of retuning and calculating the whole process together. But when you create some of those isolation factors or circuits, then you can deal with like the true concept of the Tesla shuttle circuit, where you have these, what Barrett called cul-de-sacs. So you have these kind of independent parts of the circuit, and if you make them isolated enough, then you can take them at will, and that's the ideal, when you don't have to be so insecure about your input, and it just runs, and then you're just taking things at will. So there's a balance to that, and a knowledge base for that kind of thing. But initially what you'll find is you'll produce too much energy and have to kind of deal with it. But anyway, that's neither here and there. That has nothing to do with the basic kit in and of itself. But this is an excellent trigger or prime mover for that thing. And we'll also get into tuning a Arduino board for people. I don't have that service available right now, but we'll have it so that if you want a certain RPM, we can give you we have already the code that can lock in an RPM. So have the motor run at an RPM, not obviously the highest possible RPM, because as the batteries discharge on the input, you won't be able to get up to that point. So maybe lock it in at a lower RPM, say like 400, instead of this running at 500 hertz, run it at 400 hertz, and then do all your tuning for that frequency. And what makes this circuit better than the old SSG transistor circuit is that you can do that because it's all by the computer program. Whereas the other one, you've got this trigger coil that is tricky to lock in a frequency. So you lock in the frequency, then you can do all that. And again, we can do the same sort of things on the output of the generator coils here. So there's a lot more to this than people have realized. You know, I shared all these kinds of things many years ago, like say 14, 15 years ago on these groups and forums with the transistor setup. Now we're showing it with the MOSFET and the Arduino to make it real basic. And then the sky's the limit of what you can do. You know, a lot of you are programmers and can design your own code. We don't give out the code. We'll program it for people. But at this point, we're not just throwing the code out there for several reasons. Anyway, that's that. A couple of things about the instructions, I guess. Watch the amperage. I would not go over about 8 amps on this set, depending on, you know, the temperature of your ambient temperature. You can have some thermal runaway, and you don't want to melt down the coils, because eventually that would just melt the frame and that would be ruined. So you want to watch that. You could probably get up to, if you drill some holes, like if you pop off those rotors and you drill some holes into the frame, into the frame right around the bearings, like say 4 holes, you could do some, like I've done them up to 1/2 inch or so. I think even 3/4 inch. I drilled those holes, and then it sucks the air in to the coil area, and it cools off the coils a little bit more. But otherwise, you know, it sits under a decent, a very low load at 3 amps, and then once you start loading it down, typically, you know, you'd be running it at about 5 amps or something, but it can go up to 8 amps. Just watch that temperature. Once it gets to about 110, 115, 120 degrees, then it will just slowly start building higher and higher heat. It will, you know, and have a thermal runaway eventually. So I try and keep it under usually 110. Usually they'll sit at, 3 amps. It won't go more than, it will remain pretty cool, a little over ambient, like maybe even 90 or something. And this is Fahrenheit I'm talking about. So there's a lot of options. You can look at the old videos that I've done in the last couple of years with the Variac and all that, but that's just more along the lines of conventional, not in resonance and so forth, just to get you to do something if you want to charge a battery. But that's not producing really as much as the energy kind of, if you want to look at it cycling through the input and output batteries. But as long as these maintain essentially their charge, then it doesn't really matter that this is lower, if you do it the conventional way. Once you do it in resonance, of course, you're going to get an amplification factor. Depending on the Q factor of your coil and capacitor circuit. And again, you can learn that from the other kit, the resonance kit, the book, and you can experience that. Now I think what we'll do next, now that I've kind of done this basic video, I've been wanting to do really kind of this all summer, but I've been moving. I moved twice this summer, and as I said, I was poisoned In the last 2 months, I've been recovering from that. Well, 3 months I went through that. So anyway, I want to get to the resonance coil where we do an internal secondary coil separate from the regular coils that we provide. And then we can multiply the energy out in different ways. And of course, people have been waiting for that for a while, but it's kind of waiting to see if somebody else would do that, but it doesn't seem like people want to branch out, and everybody's kind of waiting for me to show them how to do something. Some of you students, at least those on the internet, the ones off the internet, are doing their own thing, no doubt. But it used to be, when I did the SSG kit years ago, people would do all these experiments and show them online, and there was thousands of people doing things. But I think those years are gone. There's nobody left on the internet doing stuff. Anyway, whatever. So that's that. What I'll do is I'm going to be getting also into the bigger motor as well. So I'll probably show some videos along those lines that some of you are waiting for. So again, this wasn't some attempt to show some big demonstration. It was more or less to show the basics of the assembly. That gives more of a visual for people to see the exact wire arrangements and the nuts and bolts of things beyond the physical diagrams. So you can watch the other videos to watch this motor that I've shown over the years. Now again, you're going to see the motors that we've had more recently have had the bigger coils this summer and for the last year or something, because I ran out of the smaller coils. And then I had some friends of mine in China make these coils here, and so we have a bunch of those right now, and hopefully we can get more of those. But in the meantime, we have the bigger coils. They're a little bit harder to place in the framing. You got to really kind of work it, but they're good and solid once they're in there. So really, it's the same thing. If you have any questions, just write me an email or give me a call, actually. So thanks for watching.